Now that we've completed chapter 1 on reviewing quadratic equations, we are going to move into chapter 2. And chapter 2 is talking about polynomials and polynomial functions. So for today, lesson 2.1 is just talking about using properties of exponents. And so a lot of this has to deal with simplifying exponential problems as well as being able to use scientific notation. So hopefully most of this will be review for you. To help you, I would recommend following along on page 88 in your textbook. You'll notice that you have the properties of exponents page. And so it's talking about the different properties that we have when we have exponents and some shortcuts we can take with them to kind of simplify how we evaluate these problems. So please review these. Again, it's supposed to be review. If you need some time and you want to copy this down into your notebook, as you listen to these videos, at any point, pause. That way you can copy what's on the screen for your own notes, and then when you're ready, you can pick it up again. You can always, of course, review something, rewind something, play it again. It's entirely up to you how you process what goes on in the lecture videos. Much better than timing it in class. Let's take a look at our first example. And example 1 is about evaluating numerical expressions. So our first problem is -4 times 2 to the 5th power, and then all of that squared. So using the power of a product property, we can distribute that squared, that exponent that's on the outside, to both the -4 and the 2 to the 5th. And then again, using power of a power property, we can say that 2 to the 5th squared is also saying the same thing as 2 to the 5th times 2, which makes it 2 to the 10th. And then, of course, -4 squared is 16. So when we simplify, we end up with 16 times 2 to the 10th, and then we can type that into our calculator nice and easy, and it gives us 16,384. When we have a negative exponent, a shortcut is when we distribute that negative exponent, it makes whatever was in the numerator now in the denominator, and whatever was in the denominator now in the numerator. So basically, you're flipping the fraction. You're making it the reciprocal. We also call it the inverse. So notice that 11 to the 5th power over 11 to the 8th power now is 11 to the 8th power over 11 to the 5th power. And then the quotient of power properties says that we can subtract the exponents. If I'm dividing exponents that have the same base, I can subtract the exponents, giving me 11 to the 3rd, and then I can evaluate that with my calculator saying 1,331. All right, scientific notation. A number is represented in scientific notation if it's in the form of C times 10 to the nth power. And C has to be a number between 1 and 10. It can be equal to 1, but it has to be less than 10. And then n, of course, is an integer. Whether it's positive or negative, it's an integer of some kind. So when you work with these numbers in scientific notations, the properties of exponents can make the calculations much easier. So let's take a look at an example. Locusts. So a swarm of locusts may contain as many as 85 million locusts per square kilometer and cover an area of about 1,200 square kilometers. So how many locusts are in such a swarm? I'm already creeped out about the part of the 85 million per 1 square kilometer, and then you want to put 1,200 square kilometers? Oh dear God. So the solution, of course, is we can take these numbers and multiply them together. So the locusts per square kilometer times the number of square kilometers will give us the total number of locusts. So substitute our values in. We have 85 million per 1 square kilometer times 1,200 square kilometers. Now, writing it in scientific notation, we can replace the 85 million with 8.5 times 10 to the 7th power, and the 1,200 with 1.2 times 10 to the 3rd power. Then, using our multiplication properties, I can rearrange this problem and put 8.5 times 1.2 together, and then 10 to the 7th times 10 to the 3rd together. Multiply them out, and simplify your exponents, we end up with 10.2 times 10 to the 10th power. Now remember that scientific notation means that the first number, that 10.2, needs to be between 1 and 10. So if it's greater than 10, we have to simplify it. So replace the 10.2 in scientific notation, making it 1.02, so 1 and 2/100, times 10 to the first times 10 to the 10th power. And then again, just combine those base 10s. So we end up with 1.02 times 10 to the 11th. So in scientific notation, that's how many locusts are in the swarm, a typical swarm. And then if we were to write it back in standard form, that would be 102 billion locusts. Billion with a B. That's a lot of bugs. Ugh. Kind of creeps me out. All right, let's move along to example 3, simplifying expressions. So here you notice that we have b to the -4th times b to the 6th times b to the 7th. The great thing is that they're all the same power, or sorry, the same base, not the same power, but they're all the same base, so that means we can just go ahead and add those exponents. So -4 plus 6 plus 7 would equal 9. So my equation has simplified to b to the 9th power. If I have r to the -2 over s to the -3, or sorry, s to the 3rd, and then all of that is raised to the -3 power, first thing I'm going to do is I'm going to distribute that -3 to both the numerator and the denominator. Then I'm going to use my power of a power property and multiply those exponents together. So -2 times -3, and then 3 times 3. And then my negative exponent property means that if it's negative in the denominator, it becomes positive in the numerator. So I'm going to move it up to the numerator, and then r to the 6th was already positive. So we are now simplified. All right, getting a little more complex, let's take a look at what happens. What I like to do is try and simplify as much as I possibly can in the first place. So to me, I see 16 and 2 can be simplified, becoming 8 over 1. So obviously the 1 becomes invisible. And then technically speaking, what's happening with that n to the -5th over n to the -5th is that we are using the quotient of powers property, meaning we are subtracting the exponents of -5 minus -5. But of course we know that means it's going to become 0. So 8 times m to the 4th times n to the 0, well, anything to the 0 power is equal to 1. So we replace that n to the 0 power with 1, and then 8 times 1, of course, is 8. So this simplifies to 8 times m to the 4th. Now, if I were writing this out, I would actually just go ahead and cancel n to the -5 over n to the -5, just because they are exactly the same. And if they're exactly the same in the numerator and the denominator, they can factor out. All right, let's take a look at a real-life example. So again, talking about astronomy, as you'll remember from the electives showcase, we do offer an astronomy class next year as we start to offer physics in the 11th grade science curriculum. So it's pretty exciting. Betelgeuse is one of the stars in the constellation Orion. So you'll notice that in the right-hand picture, we have the constellation Orion, noticeable by the 3 stars in the middle representing Orion's belt. And then Betelgeuse is in the upper left-hand corner. Its radius is about 1,500 times the radius of the sun. So how many times as great as the sun's volume is Betelgeuse's volume? So again, we're recognizing that stars generally follow spherical patterns, like a ball. So, algebraically, we're going to let r represent the sun's radius, and so that then 1,500r, 1,500r represents Betelgeuse's radius, because it's 1,500 times the size of the radius. So then set up the ratio of Betelgeuse's volume to the sun's volume, and we know the formula, although we didn't practice it in geometry this year, we'll do it next year. The volume of the sphere is 4/3 times pi times r to the 3rd power. So we can substitute that in, And then the r that's in the volume formula, we would replace with the radius that is in our formula. So Betelgeuse's volume, the radius would be 1,500 r, and then r to the third power. Now I notice that I have 4/3 pi in both the numerator and the denominator, so in my mind I'm already subtracting that away. But first we do want to simplify that cube, that third power that's on the outside of 1,500 r in the parentheses in the numerator. So we distribute the 3, so notice that the 4/3 pi has been canceled off in the numerator and the denominator. We have 1,500 to the third power times r to the third power over r to the third power. So using our quotient of powers property, or basically recognizing that r to the third divided by r to the third would be 1, we end up with 1,500 to the third power, and then we evaluate that using our calculator, and the answer is 3,375,000,000 times. So Betelgeuse's volume is about 3.4 billion times as great as the sun's volume. So that's pretty substantial. This is it for our examples on lesson 2.1. So again, review some of these examples. In your textbook, you have some guided practice questions. I recommend doing those to see how much you've already understood. And then in class, we will continue with some application processes and some real-life application as well.